4.3 Network Flow Problems. So for this section, we're not really going to be talking too much on proofs. So if applications is more of your interest, then this section may be a little bit of interest for you. So to start us off, let's go ahead and just consider some type of scenario here. Let's say I'm working within a city, and notice here I have different buildings, and here I have a start point and an end point, and I have this directed graph essentially. Let's say that these are all one-way roads within my city. And whenever I'm dealing with roads, then there is some upper bound on the capacity of cars. There's a limit on how many cars that this road can handle, let's say every minute. Let's say if I were to assign some upper bound on the limit of how many cars each road can handle. So for example, if I look at this first road here, it's a one-way road from this building to over here. And let's say it usually can handle 10 cars every minute. Not a very high amount. Let's just say we're working in a pretty small city overall. And then I can see all these other one-way roads and then how their capacities. So whenever I'm looking at this picture, one question I might be asking is, let's say if I'm transporting materials from the start point to the end point, what is the maximum number of cars that I can transport from point A to point B under these limitations? So this is a very broad example. I am leaving out some details here. Of course, there's more factors that we would usually account for in the real world. But what I have here is essentially what we are going to call a network. So, our first definition for today. A network is a digraph. Remember, digraph meaning for directed graphs. My arrows have a direction. With a non-negative capacity on each edge. A fixed source vertex, here let's call it X. And actually I think I'm going to change this notation to S in a bit. And a fixed sink vertex T. Alright, so I have a source and a sink. So the next definition I'll introduce is the flow. The flow F assigns a value F of E to each edge. In particular, whenever I'm working with a digraph, I can say, well, my flow F plus V is the total flow on the edges leaving the vertex, where F minus is the total flow on the edges entering my vertex. So we've talked about flow and capacity. Now, if I wanted to look at a specific flow, one thing that we may be interested in, is this a feasible flow? Or sometimes you might even hear some people say, is this a viable or possible flow? So a flow is feasible if it satisfies the capacity constraints. 0 is less than or equal than F of E, which is less than or equal than the capacity. For this capacity constraint, this one makes a little bit of sense. I don't want the flow of this edge to exceed my capacity. My capacity is supposed to be a limiting upper bound on this road or a one-way direction for each edge. I also want to check and make sure that I'm following my conservation constraints. That is, the amount that is leaving each vertex should be equivalent to the amount entering my vertex. I don't want these two numbers to be different from each other. And this is for every vertex that is not my source or sink vertex. As I said, I did make a slight typo here. This should be the source vertex S and sink T, which is why this is S and T here. So we have the capacity of a flow, or capacity of an edge, and then the flow value of each edge. If I look at the value of my flow overall, this is the net flow into my sink T. So if I look all the way over to my sink, my end point, the net flow is how much is entering my vertex, subtracting how much is leaving my vertex. And then a maximum flow is a feasible flow of maximum value. In other words, for this section, we're looking at an optimization problem. We're looking at how can I maximize our flow into a certain sink vertex. So here I'm going to pull up just a random network, for example. So here I have a network, and you notice here that we have our digraph each of these edges have direction going either forward or backwards, depending on what we are interested in. And notice I include these little numbers in each one for each edge. Well, for what do these numbers mean? So let's look at this top one, 0 over 1. Depending on which textbook or which paper you're reading, they may use slightly different notation, but for our purposes, we'll use the notation presented here. So whenever I have 0 over 1, what I'm going to call essentially like my numerator, this top number, this is the edge flow, the flow of this single edge. And then the bottom number will represent our capacity. Remember that we do not want our edge flow to exceed our capacity. You can imagine this as if I was looking at a water pipe. A water pipe can only transport so much liquid within any given time. If that flow is exceeding the capacity of my pipe, well, you end up with a burst pipe. So that was our capacity constraint. All right, so now that we know some general notation, what a network may look like, let's go ahead and introduce some other definitions. The next definition I'm introducing is an F augmenting path. So we've talked about augmenting paths before, and we saw that usually, more or less informally, whenever we talk about an augmenting path, it was a path that was not necessarily the most optimal or best option for our path. So, given a feasible flow F, that is something that's viable in some network N, an F augmenting path, a flow augmenting path, is a source to sink path. That is, I start at my source, and I take some type of path to end up at my sink, the ending point. Let's call this path P, such that if I look at each edge along my path P, then it follows these two conditions. If P follows E in the forward direction, that is, I'm going along P and then the direction is going forward, then I always want to make sure that my flow is less than my capacity. Again, I don't want my flow to exceed my capacity. Now, if I'm working in the reverse direction, let's say I'm moving along my path, whatever type of way, and I end up at some reason that I have to use the reverse direction on an edge, then I want to make sure that my flow is strictly positive, that is greater than 0. So, if I have an F augmenting path, or just a path in general, one other thing I want to talk about is the tolerance of this path. So, I'm going to introduce some notation here. Let epsilon of an edge, or epsilon of E, be its capacity minus its flow for any forward flow. And then if I'm working with a reverse flow, that is the backwards reverse direction, we're just going to let epsilon be the flow itself. The tolerance of my path is the minimum among all of these epsilon values. Now, sometimes you might hear me say, or if other people say, the bottleneck capacity. One way that we can think about this is that epsilon is essentially our excess capacity here. Here we see that it's capacity minus F. The tolerance will be, the path will be my bottlenecking capacity, meaning if I go along all of these edges along my path, how much excess capacity do I have remaining among all of my edges? So a lot of these terms may seem a little bit abstract, but you're going to see what I mean as I go through our example in our algorithm in just a moment, probably a couple minutes. So we have the tolerance, or some people even say the excess capacity of the path. So the next definition I'll introduce, again, before we can really start getting into these examples, is just a quick source sink cut. Remember in 4.1 we introduced an edge cut. Here, a source sink cut. Here we use the notation S, T. This consists of the edges from a source set S and a sink set T, such that my source is in my source set, my sink is in my sink set, and whenever I union S and T, I get all of the vertices of my network. So the capacity of a cut, denoted by cap S, T, is the total capacities of the directed edges that start in S and end in T. So I have this picture here. Here I have S, I have T, and then I have my source set S, and then my sink set T. So these edges here form my source sink cut. In other words, if I were to delete these, then I would actually result in a disconnected graph in particular. So if I want to look at the capacity of this cut, first off, I only care about the capacities of the edges that start in S and end in T. So in other words, this edge would be included, its capacity. This edge, its capacity would be included. This third edge right here, I would not include its capacity. Again, I'm only caring about the edges that start in S and end in T. This edge in particular starts in T and ends in S. So I'm not including it in my capacity of the cut. And then this fourth edge will be included because it starts in S and ends in T. So just a quick definition about the source of sink cut and its capacity. So why did I introduce this definition? Now we're going to talk about a major theorem in a network theory. So we have the max flow min cut theorem, and it's by Ford and Fulkerson in 1956. So if I have any network, the maximum value of a feasible flow should equal the minimum capacity of a source sink cut. In other words, if I know the max value or the capacity, then I can find the value of my other value of interest. So this is going to be important because, for example, how do I know if my feasible flow is a maximum flow? How do I know that this is the most efficient flow that we want to work with? So we're going to be using this theorem. So now we can finally introduce our algorithm. How am I going to apply this? So just like any algorithm, we're going to be dealing with a very long and involved algorithm that looks like it has a lot of text, but we're going to break it down a little bit and see how do we do this if I had an example. So theorem 4.3.1, and yes, this was intentional that this is 3.1 and then the previous one was 3.2. This is the Ford-Fulkerson labeling algorithm. So this algorithm is going to tell me if I have some given feasible flow, is this a maximum flow or is it an augmenting flow? That is, can I improve this flow or not? So as per usual with any of our algorithms, we have our initialization, iteration, termination requirements in our output. So our initialization is the RB, the source vertex S, and S be equal to the empty set. And actually, some of this notation is going to seem a little bit familiar. We're going to use R to represent our reached vertex, while S represents our searched vertex, or vertices. So we've used this notation before about searching and then reaching. So for our iteration, each iteration will consist of the following. We arbitrarily choose some vertex that has been reached but not searched. So once I fix that vertex, I look at the edges that are incident to it. For each edge that exits my vertex V, that is, it's leaving V, with flow less than capacity, and assuming that we're working with an edge that goes to something that we haven't reached already. Then we add that neighbor to R. That is, we reach that vertex W. For each edge that enters V, that is, it's heading towards V with a positive flow and something that hasn't been reached, then we add U to R. So these conditions, they may seem a little bit weird, but we actually mentioned these earlier in our tolerance conditions. Again, we're trying to find an augmenting path. So after I mark my reach, then I want to make sure that I record the path that I used to get there. After I explored and checked every edge under these conditions, we're going to add V to S. Notice here that I put the little note, we're adding it to S. We're not transferring it over. Whenever I add it to S, it means that I have reached it already and I have searched this vertex now. And now we're just going to basically keep on repeating this iteration until I reach my sink vertex, that is, I reach my end goal, or until I no longer am able to reach my sink. Depending on this outcome, it's going to tell us, do I have an F augmenting path? In other words, can I improve my flow? Or if I can no longer reach my sink, this tells me that the flow that is currently present will actually be a maximum flow. That is, I use as much of my capacity as possible. So let's go ahead and actually put this into practice. Example 4.3.2. Suppose I want to find a maximum flow on this given network N. If I want to do so, I'm going to follow two major steps. I'm going to apply my algorithm to see if I have an F augmenting path. If I have an F augmenting path, this implies that I can improve my flow. I can make use of my remaining capacity. After I identify an F augmenting path, based on that excess capacity or the tolerance, I'm going to increase my flow along that path. And then I'm going to keep on doing that repeatedly over and over again until I know I have a maximum flow. Again, I know I have a maximum flow once I can no longer reach T, in my algorithm at least. So, in other words, for this algorithm, we're going to have a fair amount of iterations and a fair amount of repeats of the algorithm. I believe actually we're going to repeat our algorithm 3 times with iterations, each one having about 3 to 4 iterations. All right, so let's go ahead and start this off. Here I have a network, and I'm going to go ahead and say let's start with a 0 flow. So how do I find the maximum flow on here? Let's start off with our first algorithm, iteration 1, so A.1. By our algorithm, we start with letting S be an R. So we've already reached S by default. So the algorithm states for edges exiting S, in other words, leaving S, I want to look through the edges where flow is less than capacity. Well, my 2 edges here are both leaving S, and we can see that the flow values for each one is less than the capacity. So here, flow of 0 is less than capacity of 2. So I'm going to highlight both of these. And by highlighting these, I can add these to my reach. So this explores all the edges of S that have not been explored already. And then, hence I have searched through S. That is, I add S to S. I have searched it, completing my first iteration of the algorithm. Now I can continue to iteration number 2. So, for iteration number 2, I must arbitrarily choose some vertex that is in R, but not in S. In other words, I'm going to choose a vertex that has been reached, but not searched yet. So arbitrarily, let's go ahead and choose this top vertex. I could have chosen this bottom one, but either or, your steps may look a little bit different, but we should end up with similar results at the very end of all of these algorithms. So let's start with this top one. So I fix this vertex, and I look at all the edges that are exiting or entering this vertex. In this case, I only have one edge that has not been accounted for, where the neighbor hasn't been accounted for. This is an exit edge. It's leaving this vertex. So for exit edges, I need to check the ones where flow is less than capacity. Well, here 0 is less than 1, so I can include that. Therefore, I can reach this next vertex. And then that's my only edge. I've checked all of my edges already. I don't need to go backwards because I don't care about the neighbors that have been searched or reached already. So now I can add this to S. All right, so we've completed our second iteration. Now let's continue with a third iteration. Again, I can arbitrarily use any vertex in R but not S. So I could use this bottom vertex next, or I can use this top one. So what I did is I just arbitrarily chose this top right one. Let's search this vertex. So if I go ahead and look at this top vertex in the right, here I have a little bit of an animation error. This should not be showing up just yet. If I search this over, then I'll look over and see that I can reach T. Once I reach T, then my algorithm states that I should terminate my algorithm immediately. So again, this S was not intended to be here. This should have been this edge went out first, and then I reached my sync vertex. So if I look at this, I have now reached T, and now I want to observe the augmenting path of this flow. That is, how did I go from S to T? So if I do that, I have these top three edges. So now we're going to look at our excess capacity for each of these edges. That is, what's our epsilon value? Remember, for forward edges, since they're all forward edges, epsilon is the capacity minus the flow. So for this edge on the top left, I have 2 minus 0, or 2. Here I have 1 minus 0, or 1. And here I have 2 minus 0, I get 2. So my epsilon is my excess capacity that has not been used by the flow. Now I can calculate the tolerance of this path. In other words, what is my bottlenecking limit? Remembering that the tolerance is the minimum among these excess capacities. So the minimum between 2, 1, and 2, I get 1. So since I have a remaining tolerance, this tells me for all of the flows along this augmenting flow path, I can adjust this and actually improve my flow by adding the tolerance to each of these flows. In other words, these are all going to go from 0 to 1. Thus, I've completed my first algorithm under 3 iterations. So now I'm going to repeat the process right from the beginning. Now I have a new flow from including these 1, 1, 1 on the top. And now how do I know if this is a maximum flow? Is it my most efficient flow? Or can I improve this even further? So we're going to repeat our iteration. Let's do iteration B.1. So algorithm B, iteration 1. So we're pretty much going to go through the same process. By default, my source should be in R. I explore from edges from S. For the forward edges, I want to make sure that my flow is strictly less than capacity, which happens for both of these edges. Again, for this top one, even though I changed the flow is still less than the capacity. And by marking these edges, I can mark the vertices as reached, and S has been searched. So we are done with this this first iteration. Let's move into iteration 2. So for iteration 2, again, arbitrarily choosing any one of these two, let's start with this top one. So the only neighbor that has not been accounted for is this one over here on the top right. And remember, for the forward edges, I'm only accounting for forward edges where flow is less than capacity. Well, if I look at this edge, the flow is not less than the capacity. In other words, I can't use this anymore. You can imagine that I've already filled up this as much as I could along this edge. So therefore, I'm not going to highlight this edge like before. It's already full. Well, since there are no other edges that we can explore, we've searched this vertex. We've completed iteration 2. Moving from here, now let's look at this bottom vertex. Now I'm going to look and see among all of the edges or all the neighbors that have not been accounted for or not reached, I want to see for the forward direction, where is my flow less than my capacity? Well, for this bottom edge that's moving out, I can see that my flow is less than capacity, so I can include it and add this to my reach. What about this other edge here? Well, since it's a reverse edge, it's not leaving this vertex, it's entering. We have to check our other condition. For edges entering my vertex, I want to check and make sure that my flow is positive. Well, for this for this edge that's entering this vertex, the flow is 0, meaning it's not positive. So that means I will not include this edge. I'm not going to reach this other vertex here. So now I've only have to explore one edge, meaning that I have searched this vertex. We have completed iteration 3. Continuing forth, let's go into iteration 4 now. So now I go to any vertex that's in R but not S. So I only have this option here. And there's only one edge with a neighbor that has not been accounted for. Along this edge, I want to make sure that since it's moving outwards, forward, I want to make sure that the flow is less than capacity. So 0 is less than 2. So I can add that in and reach T. And then now also technically we have searched this vertex. Well, since I have reached T, I can terminate this algorithm and record the augmenting path. How did I get from S to R? Well, I took these bottom 3 vertices. So this is an augmenting path. Now I must ask, can I go ahead and look at the excess capacity for each of these edges? So for this edge on the far left, the excess capacity, again, is capacity minus flow. So in this case, I have 2 minus 0, 2, 1 minus 0, 1, and then 2 minus 0. That is, I get 2. So I found my excess capacity for each of these. Now I have to look for the tolerance, which again is the minimum excess capacity among these 3 edges, which we can pretty clearly see that the minimum between 2, 1, and 2, I get 1. So using this tolerance, I look at the flow of each of these edges along my augmenting path, and I increase it by the tolerance. That is, I change these bottom 3 from flow of 0 to a flow of 1. So now I've improved my flow even more of my entire network. Alright, so again, we're not done yet. All we've done is improved it. We haven't proved that this is a maximum or most efficient flow yet. We continue to repeat this algorithm again and again until I get to that final maximum flow. Let's see what happens next here. Moving into iteration C. Again, this is, apologies, another animation error. There should be edges here. I start off with R, and again, going out, there should be edges here. Let's see if I can draw them, actually, just so that we have them available. There we are. Imagine that those lines were straight. So if I look at these, remember that from R, I look along edges for the exit edges where flow is less than capacity. Well, for both of these, my flow is still less than capacity, so I can go along both of these. There we go. There are my lines. All right, so since I can reach them, I put them into my reach. And also, I've searched S. Now I can arbitrarily choose either vertex in R, but not S. Again, just arbitrarily, I'm going to go ahead and choose this top one. If I look at this top vertex, I can see for any edges exiting this vertex, I only care about the ones that have flow less than capacity. Well, we've seen this before. Along this edge that's exiting, flow is not less than capacity, meaning I can't improve that edge anymore. Thus, I can go ahead and say that I've searched this vertex. There's no other edges to consider. Now let's move to this bottom one. We're pretty much going to do the same deal. If I look at this bottom vertex in iteration 3, for this forward edge, I will not use it unless flow is less than capacity. But here flow is equal to capacity, so I cannot use this edge. So this forward edge cannot be used. And then what about this backwards edge? Again, for a reverse edge, one that's entering my vertex, I only use the ones where flow is positive. Here my flow is 0, so not positive, so I cannot use that one as well. Hence, neither of these edges can be used. Thus, after searching all the edges, I can put this into S. In other words, what we've just shown is that I can no longer use these edges because I've already maximized their capacity. So, here I have these 3 vertices on the left are both all in R and S. Remember that this was our other termination condition. Either I reach T or R and S become the same set. Well, now that R and S are the same set, let's go ahead and circle this. Let me change the picture real quick. So these 3 vertices were in S, and then these remaining vertices were, well, not S. So if I look at this S and not S, or S bar, let's look at the edges between them. Right here, what I've highlighted in orange or glowing, this is our source sink cut. Remember the source set was a set containing S, and then my sink set was a set containing T, and then my cut was the edges between the 2 sets. So in accordance to the max flow min cut theorem, if this is a max flow, then this should be equal to the capacity of my cut. So if I look at the capacity of this cut, let's see, remember for the capacity of a cut, I only care about the edges that start in S and end in S bar. So this top edge, yes, we will include the capacity. We'll include that capacity. Well, with this middle edge? Well, this middle edge starts in S bar and ends in S. We want it the reverse direction, so we don't want to use this capacity. And then for this last edge, it starts in S, ends in S bar, meaning we will use the capacity. In other words, the capacity of this source sink cut will be 1 plus 1, giving me 2. Now let's check the value of this flow. Remember, the value of the flow is I look at my sink vertex, and I look at the entry and exit of this. Let's see, the entry flow is 1 plus 1. And I don't have any exit flows from here, so the total value of my flow that I've written here must be 1 plus 1 or 2. Therefore, this should give me a maximum flow. The capacity of my cut is equal to the value of my flow. Since these are the same, my flow F must be a maximum flow. In other words, I can no longer improve this flow based off the capacities and constraints that we were given. So for this idea of networks, this is actually a pretty big applied topic of graph theory. You may be thinking of an application of this. An application may be, let's say you're looking at your home internet service, and how much can your router really handle? Well, in the background, the way that they calculate how much your internet speed will be, they take a look into what connections does your neighborhood have, what is the capacity that your internet router modem can take, and everything like that. So this is a really nice application of graph theory that has some connections to connectivity. But besides that, this is all for this video. I'll see you for the next one in Module 5.